Welcome. My name is Ron Papa Schmidt, and I'm the creator of the Net Zero Now YouTube channel. This is going to be video 10A. It's going to be in the science section, and we're going to cover atmospheric circulation. And this is really going to be part one. We're going to make it a two-part series because it's just too long otherwise. And so we're going to try to address two fundamental questions. The first one is, what is the structure of Earth's atmospheric circulation and how does it operate? And the second question is, how does climate change impact Earth's atmospheric circulation? Now, this is going to be a little bit of a scientific presentation, so we're going to delve into how this basically works. So it's going to be at a pretty high level, okay? And it's going to be a pretty basic presentation. But this presentation may not be for everyone. But if you really want to understand what's happening to our weather and maybe get an appreciation for what you hear on our weather newscasts and other kinds of things, and why we have tropical rainforests in some parts and deserts in other parts, etc., I think you'll find this really probably pretty interesting. So I encourage you to sort of hang in there if you periodically find it being a little bit too scientific, okay? And I'll try not to keep it that way. Okay, so let's start. So we're going to have two parts of this presentation, as I mentioned. Part one, we're going to talk about the following major components: the Hadley cell, the Ferrel cell, and the polar cell, and the related wind patterns. And you can see those on the diagram on the illustration on the left. And then the second presentation is going to cover the Intertropical Convergence Zone, the horse latitude, polar front and jet stream, and the troposphere and the tropopause. Okay? Now, what you see here is basically a picture of the illustration of Earth's circulation systems. So let's move over first and talk about the major characteristics of atmospheric circulation. So the first one is atmospheric circulation is a large-scale movement of air that distributes heat and moisture across the globe. It really drives our weather patterns and creates sort of our unique climate zones. So I live in Columbus, Ohio, so while we have one weather system here, pattern here, that's different than what occurs in Arizona, that's different than what occurs in Brazil and other things. Well, what causes that is really this atmospheric circulation. So it's really very important, okay? The second thing is that the primary cells that drive this, and you can see on the illustration on the left, are the Hadley cell, the Ferrel cell, and the polar cells. And they exist in both the northern hemisphere and the southern hemisphere. And you can see them named here. And what we're going to do is we're going to go through each one of those individually and talk about them in more detail. So I'm not going to cover that now. And then each one of these sort of cell areas has a corresponding surface wind pattern to it. And some are called the trade winds, the westerly, and the polar easterlies. So the third thing here is that the key driver of atmospheric circulation is uneven solar heating. And by that we mean, for example, the temperature at the equator is significantly higher than it is at the pole. And the temperature gradations change with latitude. And it's those uneven temperature patterns that drive a lot of the circulation that goes on here. And the other thing that affects it is the fact that the Earth is spinning at about 1,000 miles an hour. And that's called the Coriolis effect. So those two things are what really are the fundamental engines, if you want to call it that, behind our wind patterns here on Earth. And then atmospheric circulation impacts global climate through the redistribution of heat from the tropics to the poles. Okay, it's very hot at the tropic, it sort of moves that heat towards the poles. And this determines precipitation patterns and creates our daily weather. And then finally here, the Earth, because the Earth's atmospheric circulation is primarily driven by temperature levels and differences, climate change and its increasing temperatures alter the historical circulation patterns, causing changes to the location, frequency, and the intensity of our weather. Okay, now I'm going to cover one comment, sort of the last comment on each one of these sections about a particular topic. I'm going to talk about how climate change impacts that, and this sort of globally gives you a sense of how it impacts atmospheric circulation in its entirety. The next slide here, I want to just show you this graph because I know I really have trouble relating to where the equator is and 30 degrees latitude or the horse latitude is or the polar front is. So I want to show you this graph so you get a sense of where that is. So when we talk about the equator is basically runs across the northern part of the southern hemisphere. The 30-degree latitude, or the horse latitude, sort of runs at the northern part of Florida and the very bottom of Texas and New Mexico and Arizona. And you can see that from the graph here. And then the 60-degree, or polar front, sort of runs through northern Canada and maybe just at the very southern tip of Alaska, as you can see from the graph here, okay? So I wanted you to just get a sense of that. Then the second thing I just want to talk about, you've seen this slide many times, okay? If you've watched any of these presentations, and this is temperatures are rising, okay? And that's shown by the graph on the right. But what's important here is that temperatures are rising, of course, in all areas, but the temperatures on land are rising faster than the temperatures over water, so they're higher. And the other thing is temperatures in the Arctic are rising even faster. And if you take a look at this heat map on the left, look at the very top and see that dark color up there? That means that in the last 50 years, the temperature in the Arctic has risen 7.2 degrees Fahrenheit in just 50 years. So there is a lot going on here in terms of what's happening to our temperature and our temperature distribution across the pattern, across the Earth rather, and that is going to have some impact, obviously, on atmospheric circulation because that's what drives atmospheric circulation. So let's get started on the first cell here, which is the Hadley cell. So let me just read this. The Hadley cell is large-scale atmospheric circulation pattern in the tropics that transports heat from the equator towards the pole, okay? And it's sort of identical convection loops in both the north and the southern hemisphere. And that influence global weather patterns. And the formation, in this case, in this area, in the Hadley cell area, the formation of rainforests and deserts, because they sort of occur within these areas. And there's a reason for that, and that'll become a little bit more obvious as we move on here. The second thing I want to point out is that there's something called the intense solar radiation really caused at the thermal equator causes that heat causes air to rise, okay, and that's called the fancy name for it is the Intertropical Convergence Zone, excuse me, or the ITCZ, or it's also known as the thermal equator. Let me tell you that also moves. It's not static in one place, okay? And this creates a zone of low pressure that leads to heavy rainfall, resulting in humid climate for rainforests. Okay, because there's a lot of water in this area in addition to that, if you look at the globe, and you have these high temperatures, what happens is it creates massive clouds. And these clouds eventually turn into then thunderstorms and other kinds of weather patterns, as we've talked about in another video. So some other characteristics that once the air reaches the upper troposphere, it diverges and flows towards the pole. So if you take a look at the Hadley cell up there, the top arrow, you'll see the Hadley cell, and you'll see the red arrows showing how the air goes up to the troposphere, up to the troposphere at the ITC, and then it moves towards the pole, the blue line. Okay, and you also notice, if you will, how high it is there compared to the other cells. So it goes higher in the troposphere. Why? Because the temperature is so much higher. Okay, then the next thing is as the air moves from the equator, it cools. Around the 30 degrees, the horse latitude, that's where the other blue arrow is, the cooler, dense air sinks back to the surface of the Earth, creating a high pressure area. And this happens to be coincidentally where most of the world's major deserts exist. Because of the high pressure air coming down, it's much drier. And the fifth point here is the dry sinking air at the surface then flows back towards the equator, completing the loop, okay? But the wind pattern moves from east to west. They're called the trade winds, as you can see up here. And what's causing that is the Coriolis effect. Now, here's our climate point on the Hadley cells, and that is that climate models show that the Hadley cell has been expanding poleward, which means that it leads to drier conditions in subtropic land masses such as the Mediterranean, southern Australia, and the American Southwest. Now, if you think about that for a second, remember where that sort of resides, if you remember back to the latitude thing. The Hadley cell, or I should say the horse latitude at 30 degrees sort of runs at the northern part of Florida and then the bottom tip of Texas, New Mexico, and Arizona. So as we get drier conditions and it starts moving further northward, that means we're going to see more desert-like conditions in those areas. And I think we've seen some of that with some of the wildfires and other kinds of things that are occurring. And remember, this line is just not flat. It moves during the seasons of the year. And the other thing that occurs here is that it displaces the tropical rain belts, which impact the monsoon seasons and agricultural productivity and wildfires, okay? Depending on what part of the zone you're in. So let's move next to the Ferrel cell. And this is where the bulk of the United States lives. So the Ferrel cell is the mid-latitude atmospheric circulation system, but it acts as sort of a gear between the Hadley cell and the polar cells. And its movement is not directly driven by heating and cooling, okay? But rather by the momentum of the Hadley cell and the polar cell. These are much stronger cells. And they, in turn, influence how the Ferrel cells sort of operate. Now, getting to the next point is, once you get to the polar front, or 60 degrees latitude, you can see the air sort of goes along the surface of the Ferrel cell, the red, if you look at the red arrow there, the Ferrel cell, and then it goes upward at about 60 degrees. And the polar cell's coming the other way, and both of those move upward. And that occurs when the warmer air from the subtropic meets the colder air from the polar region, and it creates a zone of low pressure, and we call that the polar front. Incidentally, the polar jet, or the jet stream, sort of resides above the polar front, okay, to give you some sense of where that might fit. And then as the air reaches the upper atmosphere, it cools at higher altitudes and then moves towards the subtropic again. And then at the 30 degree horse latitude, the air descends, sinks, creating a high pressure system. And so you can see that occurring both both that's influenced by both the Hadley cell going down at that point and the Ferrel cell pushing down, creating the high pressure system at the 30-degree level. Okay. Point 5 is then on the surface, the air flows back towards the pole. But the Coriolis effect deflects the air, causing it to move from west to east. So we call those the Westerlies at the mid-latitude level. Now, in terms of our climate statement, the Ferrel cell is really powered by contrasting temperature differences and steered by the westerly winds. Okay, so if you notice in the United States, almost all of our major weather pattern comes from the west. Okay, the circulation is also heavily influenced by wave-like variations in air pressure and the position and strength of the jet stream. So these variations in air pressure can occur not only at the polar jet, but at the horse latitude area also. These are, it's not just a fixed kind of stream. The circulation drives the formation of cyclones and anticyclones that bring stormy weather to regions like the United States and Europe. And maybe to illustrate that, let me show you the next slide here. This shows sort of the prevailing wind patterns. So the yellow arrows you see are the trade winds, and the yellow is in the northern hemisphere and the red is in the southern hemisphere. And then the blue would be the Ferrel cells. And if you notice, look at the hurricane section there, sort of towards the middle, 2/3 of the way up the chart. You can see hurricanes there. You see the yellow arrows. And so what's happening is that you have the winds are taking the hot air from Africa. They're blowing it over the ocean. And because the temperatures in the ocean are rising, we're getting more water vapor into the atmosphere. More clouds are forming, and we're getting bigger and intenser storms. Okay. But as that moves then towards the United States, it hits the westerlies. And in some cases, you notice sometimes we have the hurricanes are coming almost up the floor, and then they go westerly back out to the ocean and never really hit land. That's the westerlies that are pushing them in that direction. Again, these are not stable airs. They go up and down all the time. The horse latitude patterns here. Okay. The other thing is sometimes what happens is if the westerlies are wing, it goes all the way into Florida, the Gulf of Mexico, and then starts its westerly climb. In that case, you get these very heavy hurricanes that affect us. Now, we talked about how temperatures are increasing and how the Hadley cells are sort of moving northward. Well, as that moves northward, that means that maybe more of these hurricanes will actually get to the Gulf of Mexico and then start moving up the United States. So we might get more severe, the United States uniquely might get more severe hurricanes just because of that northward migration of the Hadley cell. Okay. Let's jump over now to the polar cells, and those are, you can see by the arrows where they're located. The polar cell is a large-scale atmospheric pattern found between 60 degrees latitude and the poles. It's weaker and smaller than the Hadley cell and the Ferrel cell, as you can see, but it's driven by sinking cold air, dense air at the poles. So this is cold air coming down that is driving it, whereas in the Hadley cell, it's driven by warm air going up into the atmosphere at the equator. So there's different things driving these two things. The other thing is that the intense cold air at the poles causes it to become dense and sinks, creating a high pressure area at the pole. Okay, the sinking air then flows along the surface latitudes towards the polar front, and the Coriolis effect sort of causes at the surface causes these polar easterlies, as they're called, and you can see that by the arrow there. At the 60-degree latitude, the cold air meets the warmer air of the Ferrel cells, forcing the warmer air and denser air to rise, creating a low-pressure front at the polar front. At high altitudes, this cold air then travels back to the poles, completing the convection cycle. Okay. And again, as I mentioned, this is where the polar jet is, or the jet stream as we know it. And that system sort of fluctuates some. So let me go to the next slide here. The high pressure systems at the pole contribute to extremely cold and dry polar region conditions, okay? The convergence of the colder air with the warmer Ferrel air leads to unstable weather conditions at mid-latitudes, especially in winter when the low pressure vortex sort of weakens, okay? And that gets to this last point in climate change. The polar cells help regulate temperature gradation between the pole and the equator, and climate change has weakened the system, leading to more unpredictable and extreme weather. If you've seen some of the presentations I did where we talked about the jet stream, you can see the jet stream now is meandering more. Well, the reason it's meandering more is the temperature differential between the poles and the equator's changing. Remember how if you remember back to that illustration, the temperature at the pole has actually gone up 7.2 degrees Fahrenheit in the last 50 years. And that's causing changes to the strengths of these systems and causing some more deviation to occur at the polar front level, okay? So let's wrap this up. So this is the end of 10b. So what we've done here is we've talked about the Earth's atmospheric circulation, and we primarily focused on the Hadley cell and the Ferrel cell and the polar cell and the related winds that go with surface winds that go with them. In 10b, you can see the visual for that presentation. It's going to cover the Intertropical Convergence Zone, or the thermal equator, the horse latitude, the polar front and jet stream, and the troposphere and the tropopause, okay? Now below that, if you've not know how to get at these videos, that is the QR code that will take you to the YouTube channel, the Net Zero Now YouTube channel. So as we wrap this up, I think it's pretty obvious that the changes in temperature are having an impact on our weather patterns and Earth circulation. Hopefully you can understand that now after watching this portion of the video. I think you'll even get a better understanding of that if you watch 10b. And what that means is that we really need to pay attention to what's happening to our temperature and what's driving it, which is why I'm so passionate about getting net zero greenhouse gases to net zero as fast as humanly possible, because that is the only way to control this. If you take a look at the scale of these systems, okay, that we've talked about today, if it isn't obvious to you, it's not something that a quick technology fix or some billionaire with a new idea is going to be able to magically fix. These are massive, massive systems. And there's nothing human beings can readily do to quickly fix all the problems we're creating by higher temperatures, okay? And I guess that gets to the last point. And my favorite group is the Eagles, and they have a great song called Do Something. There's some of the lyrics below. And so I guess one of my other things is that I want you to do is to just do something, okay? Because the truth is, our corporate leaders and our corporate executives aren't going to solve this problem. If we're going to, they're too tied up in vested interests. If we're going to solve this problem, it has to be a bottom-up kind of effort. And so what are some things you can do? Eventually I'll create a whole video on that, but right now there's some very simple things you can do. Number one, subscribe to this channel. One, that'll make sure you'll get future videos. But second of all, it is part of the algorithm that YouTube uses to determine where they send people who inquire about net zero or other temperature-related kinds of issues. So the more subscribers we have, the more likely other people will see this video. You could rate this video, you could comment or make suggestions on how I can improve it. Please share this link with your friends and family and talk about this problem, okay? And just get involved. Just do something, okay? And just thank you so much for spending your time. I'm honored that you made it this far. Hopefully it's been worth your effort. And I hope you'll join us for session 10B.